Hey, welcome to another coding session. As always, we're continuing with Bangalang. I'm super happy with some of the progress we've made recently. And I went through the code and kind of made a list of things I'd like to do, a bunch of kind of features and a bunch of just like sort of cleanup stuff. And I kind of want to work through a lot of this. I guess I went through the source code and looked for anywhere where I felt like I had, done like a bit of a workaround because I didn't have the feature that I wanted. And so all of these should like address those and make the code look what I would call nice with the features that I want for the most part. So I thought I'd try like grabbing maybe a bigger one of these, and we'll see how we go. If we have time left, then we can do some low-hanging fruit, like some just quick stuff, maybe some cleanup or some of these things that are quite easy. So I want to do struct/slice literals. That's the thing I want to grab now. So the idea, maybe I'll just go to some source code and we'll show what my idea is. So this is the kind of thing I want to solve with it. This is me taking a raw pointer returned by C and converting it into a slice. And it's this really hacky way of doing it where really I just want a one-liner where I can go like raw equals buffer data raw and length equals vertex count, like that. So this is my literal. Because a slice is composed of basically a pointer to the data and the length. So this raw is the pointer to the data and length is the length. So I want to be able to do that instead of this. But maybe before we get to that, because slices are kind of maybe a little bit trickier. I think maybe it's easier to do like a struct first. So if I go like foo is a struct with blah, which is an I64, then I should be able to say like foo dot blah equals 7. Oh no, that's I want to do the struct literal, don't I? So I should be able to do this. I should be able to do it in one line. Blah equals 7. And then I should be able to just like print it. Eventually I want to improve this as well, because this is kind of a pain in the ass having like such a, like 4 lines just to print out something. So foo.blah is what I want to print out, like that. And I should print out 7. Right now I should get some sort of error, I'm assuming. Oh, the tests are turned on, I guess. I'm just gonna probably just like before, I'm gonna end up like committing it, comment it out, but here we go. So right hand side must be an expression. So it thinks it's not an expression. Not quite that's 65, yeah. Not quite the error I was expecting, but hey, it doesn't know what this is. Well, actually, I think that is valid code. It's kind of valid code. It's like it should give a type error because this is like a scope, right? It's a scope with one assignment in it. But it should at least give an error that it doesn't know the type of blah. But I guess before it even gets to the point of type checking the stuff, it already knows that a scope here is not valid. So that is the right error. So what do we need to do here? Let's start at the grammar. And actually we do have some stuff missing from the grammar because we did all these arithmetic things. We have assignment variations now. So if I go like that, we should have plus equals, minus equals. We haven't gone to the grammar for quite a while. I guess I just kind of forgot about it. Oh, did I skip out multiply? multiply equals, and modulo equals. Those are all valid operators now. Cool, so we have quite a lot of operators. And now I want to make a new guy, which is a struct literal. Or actually, maybe I'll call it a compound literal, because it can be, it's not just for structs, it can apply to structs and slices is what I'm going to do now, but in the future it might even be useful for arrays and stuff, the same kind of syntax. I'm just realizing now, oh no, that's got a star, so it could have multiple of them. But shouldn't they be comma separated? They should be comma separated. I'm pretty sure if I go to parse struct type, I think it's a bit below parse struct type. Yeah, see, it's expecting a comma. So should be comma separated. So let's go to our struct type. I think it should be basically the same as procedure type, which has, I guess this. How does that look? What is this? Oh, it's just, is that just saying that any kind of, the hell is that saying? I guess it's optional, so it's saying like all of this stuff in here is optional, because there could be like no members. And I guess with this struct literal, or this, oh no, this is a struct. This is a struct type, so it should have at least one member in it, otherwise there's no point. Well, it could be like just some sort of marker or something. Okay, let's also have that be optional. So, is that it? Yeah, I think that's it. Okay. So the struct type could have nothing in it, and I'm pretty sure that the current parsing thing would allow that. While it's not closing. Yeah, it should allow nothing in it. Okay. Now that we've fixed that up, let's make our compound literal, which I think is very close to struct type. Compound. Oh, my keyboard is wrong. Compound literal. So it does not need to have struct at the start. But apart from that, is it basically the same? Within curly braces. Well, no, it's a bit different because we don't do it like this. It's more like an assignment. But it's an assignment where you can only have just an identifier on the left. So do we want to do the whole assignment thing? Which could be a primary, which adds all this extra kind of complexity. I think, yeah, let's just call it an assignment. So, getting a little bit confused here. I think it's like this guy here is an assignment. And then also after the comma, there could be more assignments. Yeah, some comma separated assignments, or there could be no assignments. Let's see how that goes. So this compound literal can appear on the right-hand side. Let's put it, our right-hand side primary. Let's put it like here. All right, so I think that looks good. I'm going to make one other change up here to the statement. I'm going to move this across here, which might seem very strange, but should make sense in a second. Well, I guess I can explain a bit. Because the compound literal is curly braces with assignments in it, it's basically a scope, right? Now the comma is a bit new. A scope can't have commas between assignments. But, you know, scope and compound literal, if you have a basic one that just has a single assignment, that could be a scope or a compound literal. It could pass to both. So now scope and RHS expression, it's ambiguous which is which. So all three of these I'm going to need to pass together, I think. Let's get onto that now so it makes sense. So when we go to parse statement, I think I'm basically going to say like if type equals keyword. And so I'm not going to have this parse scope here. Instead, I'm going to have like parse scope or assignment or right-hand side expression. So it's going to attempt all three of these and choose the best one. So if we go for scope, return, here it is. So scope now, I'm move below return because I'm picky about ordering. And also I guess we should do like type checking. Fix up the order so that the world is right again. Okay. Now we can relax and we can continue. So we're going to add like a parse scope here. So that's going to be using like a scope stream, scope node, scope OK. And now we're going to choose through these which one is the best. So I'm going to say max next index equals, I found that there's this built-in max procedure. In Odin, so that is handy. So scope, assignment, and right-hand side. And we're going to favor scope first. Like I said, right-hand side and scope can now be a bit ambiguous, but I want to favor scope. So if that is like that, then we're going to say, okay, return the scope node and scope OK, and use the scope stream. So basically we're selecting scope if it has the max index. And let me bring back that old condition so I can get this right. So if these are equal, if these are the same, it looks like it's only choosing this if it's less. So it's only choosing, so it's choosing this. No, it's choosing this one when it's greater. So if they're equal, it would choose this one. So confusing. So then I think that means that that's the next one to choose, and this one we can just put like this. Okay, so that's our priority. Let's see how that goes. If we got it wrong, I'm sure it'll come up soon and we can fix it. I would sip of my trusty tea. So that's that part. Now in the when we're parsing a primary, if we come across an opening curly brace, which I think we don't, there's no such thing right now, right? I'm pretty sure. So let's put it, I think in the grammar we put it after number. So that'll be opening curly bracket. Then we want to parse a compound literal. We should make sure we all return. Like so, and we need to add this guy. So we have call, so let's put it here. Parse compound literal. And we did say that it was like very similar to this, so let's copy this code. I guess we need a compound literal type, which would go there. So we don't need that struct keyword, we took that out. And now instead of all this, it's we're parsing an assignment. And just adding that. Does member node feel right? Member, close enough, I guess. I can't think of a better name right now, so that'll do. Yeah, I think that's basically it. Now the challenge in type checking is when we're type checking an assignment, if we have, so in our example code here, we have this. See, this is, like we saw here, this is still going to get parsed as a scope, right? Because we favor scope over a right-hand side expression. So this is going to get parsed as a scope. And then I think we need to kind of see like, because the only place that a scope makes sense with an assignment is if this is a procedure type. So if it's not a procedure type, and we see a scope over here, then basically that means that this is, it should be a compound literal, not a scope. I feel like that's not enough. Like I'm sure there are going to be some situations that we come across where we're going to switch this to a compound literal, but really it shouldn't have been. Like, what if we have a situation like, what if there's also a do stuff? Didn't I say we don't need that? We don't need that line. So there's a do stuff, which is like proc some procedure. And then we do foo.do stuff equals blah equals 7. In this situation, when we're here, type check, well, we've type checked the left-hand side, haven't we? So we do know the type of the left-hand side. So we do know that this type is a procedure type. So actually that should work. So I think the idea here is like, this is the stuff that tests if it's a procedure on the left-hand side. Well, there's this is member thing here. Yeah, so I think this is probably not going to be enough right now, but I'm going to put it in this else for now. Maybe above here we'll put like, you know, if it's a scope. So I think this is way too simplified, and we're going to have to fix this later. But we'll switch it to a compound literal. What's wrong with that? Oh, just need one equals. And I think we're going to need to also, you know, if we have a compound literal, put it down here. If we have a compound literal, I think we're going to need to set the right-hand side type from the left-hand side. Do we know that that's a thing? We have not validated that it's not null. So let's say like that. Yeah, I think we're going to need that later on. So when we go down into type check primary, then down here after Boolean, we'll have our compound literal. And what are we going to do here? So we have a compound literal which has children which are assignments. And the left-hand side of those assignments, we can't just pass them to parse primary like we normally would. We need to do it specially because we need to get the types from, you know, I've made the type of this node. Where's do we grab the type node at the top? No, we don't. So the type of this node is the type of the struct or slice. So now we need to drill down into the individual assignments, and like this is one of the assignments. Let's take this away. This is one of the assignments in there, and we need to get the left-hand side, and we need to give that this type. So we need to get this type information is on this scope right now. So we need to pass down the type of information of this to this. That's the idea. Because we're going to need to use that when we get to generation. So for child node in node.children, so this is the assignment node. I guess we need to, at this point, verify that it is an assignment. If child node.type is not, I hate how I don't get suggestions. So if that's not an assignment with some error handling, here we go. So failed to type check primary, and we can say compound literal compound literal can only contain assignments, something like that. So that does not actually have any parameters, so we can just cut this stuff out like that. I want to tidy this up. Actually, I don't like this, but anyway, so that's verified that we're dealing with an assignment. And we further want to restrict it. So let's get the child LHS node, which is the first child of the child node. And if that's not an identifier, yeah, what I'm trying to say here is like you can't, I can't say like, I can't index and I can't put references and dereferences. It's got to be just straight up an identifier. That's kind of the idea. So I guess to prevent something like, where are we? like dot something, I should also say that it can't have any children. And I think this is not a great error message, but close enough. So we kind of know that the left-hand side is all good now, I think. And now we want to, apply the type to the left-hand side, I guess. So let's append something. So to get that something, we're going to have to go through the child. This here has got the struct node. So its children are the members of the struct. And we find the one where we have something similar up here, don't we? How do we do it? Yeah. It's kind of like that. But it's actually this here is the identifier we're looking for. So that means we've found the correct one. So then we get the type of it. Do we need to get the result? No, let's just get type, apparently. I have a feeling we need to get the type result, actually, but I'll just copy that for now. Member node, it needs to be a pointer. Break, and if we don't find the member, then that's an issue. You know, it's an issue just like up here. So if not found member, yeah, there's not a member in what? I think in this context, we don't know the name of the thing. Like we don't know the name of the variable. So I think I'm just going to say, oh, that is not a member. Wait a minute. So this is the thing that's not a member. Okay, that's fine. All right, we do have that information. So now we should have applied the correct types. Oh, we need to say found member equals true. And now we also need to verify that there is a right-hand side node. So we need to say like the length of child node.children equals 2. Child node? Yeah, that child node is the assignment. With right-hand side expressions, I guess. It's not the greatest yet. These error messages I kind of want to review, but good enough for now. So now we get that right-hand side, and the reason that we need to get it is because we need to type check it. So we need to type check, yeah, a right-hand side expression, which is this node. What else do we need to pass? Context and expected type. Context and the expected type is, well, we've got the type of the left-hand side node now, so we should be able to go get type of the left-hand side node. But those are not pointers, so let's just make them pointers. We need to all return. Okay, so I think for a struct, that should be all the type checking, and we should have all the correct type information now. So we generate an expression. So now when we're generating, we come down. This is where we want to put it. So we have our compound literal. And what are we going to generate? So I think kind of like with a slice, we're going to need to allocate some space for it. Where do we do that? Here, for slices. So first thing we do is we allocate some space. And the last thing we do is we're going to need to return something like this. So we allocate some space on the top of the stack, and then we return that. And because we're allocating, we have like this utility procedure somewhere. Is it up a bit higher? That's generation, should be in here somewhere. Contains allocations. So I think if we come across a, what did I call it? Compound literal, then we've got an allocation. Okay, so now we've allocated space, a temporary space for this struct that we're creating. I guess we need to like loop through all of the members of that struct and see if we find a relevant assignment. And if we do, assign it into the correct place of the struct. And if we don't, then I guess we do like a null assignment into the struct. Kind of similar to, you know, like when we generate an assignment, but I don't think we can reuse that code because this is kind of quite specific. So for member node in type node, because the type node in this case is going to be a struct, right? So a member node is each of the nodes within it. And we're going to need to know where that member is. So we can go member location is, well, memory. So it's basically at the top of the stack. And then after every iteration of the loop, we need to add an offset. It's like the byte size of the type of the member node. I think. So we need like type node.children. Yeah. I think that's right, but this needs to be a pointer. Okay, so we know what member we're talking about. We know the location, so now we need to find within our compound literal we need to see if we can find it. So let's go found assignment. And if child LHS node is child node dot children 0. If that is the same as the member node value, then we need to generate an expression file for the right-hand side node, right? So this is so it's generating an expression. In this case, it's the 7, but it could be a complex expression, right? So we're generating an expression, and then we need the context destination. Context destination and register number, which I guess we have, yeah. So what is the destination? The destination is the member location, right? We need to copy it into this newly allocated space at the location of the member. Cool. Now we can break, and we can also say that we found an assignment. Now down here we can say if we did not find an assignment, then we need to do a null assignment. And generate expression has like this, all this null assignment stuff built into it. So we should be able to do this again. It's just that this right-hand side node if we go to generate assignment, there should be an example of this. Generate expression. Here we go. That's it there. LHS type node. I guess it's the type of the member node. So there needs to be a pointer. The type of the member node is what we put in. So this needs to be correct so that when we do the null assignment, we do it with the right amount of bytes. That's basically what this type of information is for. And then we go like that. Oh, that needs to be a pointer. So then anything where we didn't explicitly assign, see, so we did not explicitly assign to blee, so blee should be 0 because we have done this this assignment from nil. Okay, what happens when I run this? All sorts of errors. Expected opening curly bracket, but found number at line 61. Line 61 of standard lib. Found number. Expected opening curly bracket. I have a feeling this is to do with my parsing up here. So I guess it would have done a right-hand side expression correctly. But the scope is always going to have at least one well, it's not going to successfully get the token, is it? Opening curly bracket. So I would think that it doesn't go in there. So assignment node has no children. Scope node has 2 children. So it has an assignment. So I guess we're looking for a scope node where there's no. So here's a scope node where there's no children. Assignment also has no children. Right hand side has a number. OX3. Interesting that the OX3 seemed to work, but this one did not. It was on line 61, wasn't it? Well, but this looks like it should fail also, because it's deciding to return this. 469, 468, 469. Yeah, it thinks those are the same. But I would have thought that scope stream would not have, like this should have failed. But it increments even if, interesting. I wonder if this should go down here. You know, if we fail, then we shouldn't increment. Maybe that's better. Blah is not defined. Line 65, column 42. So that's here. So, okay. Failed to type check primary. Blah is not defined. So I think we're getting there. I think we're getting there. Blah is not defined. I guess one thing in type checking is that up here, we immediately go into the first child, which doesn't actually make sense in the context of a compound literal. Because we're doing stuff to the children ourselves. You know, we're kind of manually going to all the children and adding type information. So we probably shouldn't go to the children for that. Compound literal can only contain assignments with right-hand side expressions at line 65. So it seems to think that it just does not contain a right-hand side expression. Okay. Oh. Cool, I got that condition wrong. Let's try that again. Can only contain assignments. Interesting, because before it was getting an error here, and now it's getting an error up here. What? Probably. Because we have the type information already. See, we have the type node. So probably we want to say like that. So we want to loop through everything except for the last node. This cuts out the last node because that last node is the type and we're not interested in that. Segmentation fault. Let's see. Well, interesting. That's a bit different. Oh, look at that. Look at that. That there looks like an infinite loop. Probably because we have the type is assignment. But if we go up to the top here, well, we should not be going in here with an assignment node. That's a thing. We probably need that same condition here. So that condition that I added up here should also be there. For compound literals, we don't want to generate the children. Okay, Blar is 1, Blee is 0. I'm kind of surprised because I just realized. So that should be 7, not 1. But what I just realized is that we don't actually generate anything. So this code is like directly after this. Here. So it's like, let's check OpenGL. So it's this assignment here. Is that right? Yeah. So it's doing this, which is copying. Interesting. It kind of looks like it is generating some code. And the code is kind of what I would expect it to be, actually. Did I? Oh, I did write generation code. For some reason, I thought I hadn't written the generation code yet. But obviously, we got something a bit wrong. This looks right. So the second member, we're just copying nil to it. Because the second member, we don't specify anything. And so that's why we got the right number. But it looks like here we're saying RSP plus 140. But it's a literal. It's a 7. So that's not right. Why is it saying that? Because the right-hand side is child 1. That's probably got something to do with it. There we go, 7 and 0. Nice. Okay. Yeah, see, now we see like we're basically just moving 7 to the top of the stack, which is the start of our newly allocated struct. So that worked. I'm pretty happy with that. We have a struct working. But now, okay, and we do have a couple of places in the code where we do create structs. I don't think we have any in this code, right? I think it uses structs, but I don't know that it... No, it's got this one here. So we could go like this. Whoops. And comma separate, and that should work. Yeah, it's drawing the triangles. It's doing it like 200 frames a second, which makes me think it's doing a single-threaded version, but it's not. It's just that my laptop, performance on my laptop is just like all over the show. So that worked. I think we also have some places in here. See, there's one. We can go work account. And I think there's like one other place. Or was there not? I think that's it. Okay, cool. So let's just double check that that works. Great. Performance is trash, but that's okay. We do get like these rogue windows that never close. Need to figure that out at some point. So let's close that. I wonder if that helps performance. Yeah, performance jumped up quite a lot there. Okay, interesting. Okay, so now we have structs, but I want to get slices. I want me slices working. Now, slices don't actually have members. We have to do some kind of magic. These are like virtual members, you could say. So first, let's go to type checking, compound literal. So I think a lot of this stuff is all kind of correct. You know, it needs to be an assignment. It needs to be an identifier. Also, there needs to be a right-hand side in this stuff. It's like this stuff here is struct specific. So let's say if type node.value is a struct, otherwise, if it's a slice, and if it's neither of those, then we have an issue. It's like cannot it's like an incompatible type thing, which should actually also be already be taken care of, actually, by the type coercion. The type coercion should catch it, so I think that's fine. No, but it's not going to catch it because we took the type from the left-hand side. So it's like, we don't know if we're in an assignment, but cannot use compound literal with type, and then we'll put the type here. Okay, that'll do. Okay, so how do we do slices? What are we actually wanting to do here? Append the correct type information. So I think it's a case of like, if the left-hand side value is raw, actually I like me a switch. I like me a switch. So case raw, case length, and a default case. Default case is going to be an error. This one is not a member. And so what am I wanting? I'm wanting to append the correct type information. So for a length, it is just, I guess we don't need this actually. Length is an I64. And the raw is, so if this is a slice type, it should have the first child of that type should be what it's a slice of, which is what we want, I believe. So that should be the correct type for the raw. Actually, it needs to be a reference to this, a pointer to that. So type equals reference, and we need to add that as that child and put that there. So the raw type node is a reference with a child that is the thing that the slice is made up of. So it's a reference, so it's a pointer to an element in the slice. And then we append that type to left-hand side. I think that's right. So I think that's appending the correct type information. So now when we go to generation, we need to, so this is like looping through all the members. Member location is not going to work in this case. I kind of just realized that actually we could probably take found member out of here and out of here. And then just say like found member true in each of these. Yeah, I think that works. And I'm just wondering here how we can like, where we can sort of do the if-else between struct and slice. And both of them we need to find an assignment. This member location is really the struct member location. It doesn't really make sense in terms of a slice. But going through the children and finding the correct assignment and assigning it to the member location. But we're looping through member nodes, which we don't even have for a slice. So I think here I'm just going to put a whole separate code path. I'm not going to try and share any code, at least not for now. Maybe later it can make sense. So if we're talking about a struct, then we do this. Else, if we're talking about a slice, we can do something else. And then I think it's always good in generation to have an assert if we don't fall into any of our expected paths. So failed to generate, we're in primary, aren't we? Okay, so what do we do? Let's copy this code into here. We're going to need to change it quite a lot. So we've got like member names. Just like raw and a length, and those are what we want to loop through. We don't need to keep track of this. So where it's the member name is the same. Don't need this. So I guess we can do like a member location equals this. And then if member name is length, Then we need to offset it by address size to get the proper member length. So that's got everything. That's got member location. But now we still need member node. Well, we need a type for the member. So let's say, we'll just say unknown reference. That's good enough. So for raw, we could just say it's a reference type. And for this one, we can say that it is maybe we don't do a pointer. It is a type of type I64. What's... Oh, probably I just need to do this. And then we can just do member type node like that. Okay, so I think that should generate things correctly. If it doesn't, we're going to be in a whole world of hurt. We get our triangles. So if I just cut all this out, wow, that worked. So our slice works. That is fantastic. It's taken us about an hour to get that done, but I think that's really cool. I would also like to be able to do like access.raw. We can't do that yet, but that should be quite easy to add. So then we can go from slices back to raw pointers for going back to C. Basically, the only reason you would want to use a raw pointer is for C. That's the only reason you want to get it from a slice. At the moment, you can index from raw pointers, and I want to cut that out. I want to make it so that if you want to index into anything, it has to be a slice or an array. That's it. So pointers are just pointing to individual things. That's all they do. That's the idea. We'll get there. I don't think we have time to do that right now. One thing I want to do is like add some tests now and maybe actually run the tests. Well, that's not quite right, is it? Declare. We've got these declare, then assign. Declare, then assign array. Yeah, I guess that is. But declare, then assign slice, because here's this is a declaration and assignment of a slice. So we would need to make var1 a slice of arrays. Slice of arrays, or is it just a slice? This is a slice of arrays. And again, we have the same thing. That would be and this is then. So now this is kind of like a slice. But really what I wanted to add was some literals. Declare, then assign struct member. So let's say declare and assign struct. So that would be like this. And declare, then assign struct. I guess would be like this. And this is assigning to individual members. So that's the struct stuff. For doing a slice, it's a bit trickier because we need a pointer to something. Well, I guess we can still do it. I can do declare and assign slice from literal. So we could say var 0, var 0 is an array of 10 things. And we could say this is a slice of those things. With length 10 and raw is, I guess you could say it's a pointer to the first thing. We could do that and then verify like that. And because we like to have then variations, let's do then, which would just be this. Let's see if any of these trip up. I'm not sure about this. I think that's right. We take the first element and then we get a pointer to it, and that becomes our raw. Failed to parse, declare, then assign slice of arrays. Line 4, 1, 2, 3, 4. Ah, it should be like that. I mean, the error message was not very nice, but I think that's the point. Is that we're just declaring a variable with this type, not assigning anything to it, then we assign something to it there. Let's see how this goes. Come on, fingers crossed. We pass all the tests. We really need to do some work to improve the performance of these tests. Hey, they all passed. There was one thing that I could try. Should I do it now? Maybe we won't do it now, but I think it would be a good idea to do some inversion here so that, like, it's not these, it's these, yeah, these linear searches. If we can reduce the amount of linear searches we're doing, I think that would help at least. But I think it's not so much in the way that the tests are run, it's the compilation of the tests themselves. I think the compilation is slower than it should be. It's compiling out a lot of stuff that is not actually needed. And at some point we should get onto that. But for now, I'm just stoked that we have a compound literal for our slices and for our structs. We go like that. We don't have to have our hacky crap. There was another part of it that I had here, and remove indexing length / boundless from scalars. That's where I was saying part of that was, like if you have a raw pointer, you shouldn't be able to have it. It shouldn't be boundless. That should not be possible. So you can't just randomly index into a pointer, but it has some implications if I do that. So let's just go like that, and we'll keep that for another video, because I think we've spent enough time today. We're at an hour 10, and I'm pretty happy with where we got. So, yeah, see, look at that. That's nice. I mean, not that different, but I like it anyway. So, thanks for stopping by. Have a good one. Ciao for now.